Okay, this is an introductory video about the inequality theorem in triangles. Okay, so we're going to start with a theorem. Let's say that A and B, we have two numbers, A and B, that are real numbers. They belong to the real number set. Okay, we can say that A is greater than B if and only if there is a positive number C. So we have a number C that is greater than 0. This means that is a positive number for which A is equal to B plus C. Okay, this might sound confusing, but let's see what it means with numbers. Let's suppose that we have two numbers. Let's suppose that we know that 7 is greater than 5. Okay, this theorem is stating that there must be a positive number for which 7 is equal to this 5 and that number. So this happens if and only if, or let's use the same notation, if and only if 7 is equal to 5 added to a positive number. Okay, and that positive number, you probably guessed it by now, it's 2, right? Because 5 plus 2 is 7. So that number, C, must be 2, right? So again, if we have real numbers, two real numbers, one is going to be greater than the other if we're able to find a positive number that added to the smaller number, they will make them equal, all right? In this case, let's see another example. Let's suppose that we have that negative 10, or even a little bit smaller, negative 5, it's greater than negative 10, right? This happens if and only if negative 5 it's equal to negative 10 plus a positive number. That number will be positive 5, right? If we add positive 5, negative 10 plus 5 will be negative 5. So that number C must be 5. All right. I hope that this makes sense. And it will make more sense when we establish the next theorem. Before passing to another part of this is called the algebraic theorem. Okay. This is called the algebraic theorem. So algebraic theorem. Okay, in geometry. And now we're going to talk about something that is called the helping theorem. Helping theorem. All right. The helping theorem states that if B, so we have a point B, it's in between, it's between, all right, let me write this properly, between A and C, on the segment AC, then it must happen that AC is greater than AB and AC is greater than BC. Let's see it with a figure. Well, will probably make more sense. So this is the segment AC, and we have a point B that's in between, right? So what this theorem is telling us is that the whole segment must be greater than one of their parts. For example, AB, right? We have AB right here, must be smaller than the whole segment that is AC, right? So AC, it's greater than AB. This is what this helping theorem is telling us. And also, it's telling us that BC must be smaller than AC. In other words, AC is greater than BC, right? The whole thing must be greater than any of their parts. Okay, so this is what the theorem is stating. Let's try to prove this theorem. So to prove it, we have our statements, and we have our reasons, right? Our given is that B is in between A and C. So B, it's between A and C, right? This is our given. All right, 2. We know, and let's do the figure here. So we have it helping us understand what's happening. So we have A, we have C, and we have B right here. In between, not necessarily in the middle. By the segment addition theorem, we know that if we add AB plus BC, we add the whole segment AC. So number 2, AC must be equal to AB plus BC. This is by the segment addition postulate, right? Number 3. Obviously, since we're talking about distance, length, we know that BC, or AB for that matter, must be positive numbers. So let's start with BC. So we know that BC, it's a positive number, is greater than 0, right? So this is because distance or length is a positive number, right? We know that. But from the algebraic theorem, we know that if we have a positive number C, then this means that these two things must be an inequality in which AC must be greater than AB. So by the algebraic theorem, we know that AC must be greater than AB, right? This is by the algebraic theorem, right? And we're already done with the proof because we already proved this part. We already proved this part, right? That AC is greater than AB. And we proved the other part, basically adding the same thing. Because we know that AB, now let's do it here, AB, and let me do it with a different color so you know that we're just making the same thing. So AB is a positive number. So AB is a positive number. And the reason is the same as the one that we gave here. Distance or length is a positive number, right? And if this happens, then we know by the algebraic theorem that AC must be greater than this part BC. So number 6, AC must be greater than BC. BC. And this is by the algebraic theorem, right? So in these two conclusions, we just prove precisely the theorem. Understood? There is also a lemma for angle. Let's study that real quick. The lemma states that if ray BD separates angle ABC into two parts, so not necessarily a bisector, and those two parts, let's call it angle 1 and angle 2, right? Then the measurement of ABC must be greater than the measurement of angle 1, and the measurement of ABC must be greater than the measurement of angle 2. So what it's saying is we have this angle, all right? All right, let me draw that line a little bit better. So we have this angle, A, B, and let's put here C, right? And for that angle, we are going to draw a ray that separates the angle, and that ray is going to be called BD. And it separates us into two angles. This is angle 1, this is angle 2. It's fairly obvious, if you think about it, that angle ABC must be greater than 1. This is basically this part, right? And it's obvious that the whole angle must be greater than this small angle too, right? This part, okay? And we can prove this. Also, we can prove this. Let's do the proofs. So we have our statements. and we have our reasons, right? Okay, our first statements, it's that ray BT separates angle ABC. This is our given, right? We know by the angle addition postulate, it's pretty similar to the previous proof. By the angle addition postulate, we know that angle ABC, and let me do it here again. All right, we have it there. We know that angle ABC, this whole angle, must be equal to the addition of 1 and 2, right? So by that postulate, we know that angle ABC must be equal to angle 1 plus angle 2, or the measurements, right? So this is the angle addition postulate, okay? But by the protractor postulate, we know that you can assign a real number, a positive number, to one of or to each of these angles. And so like we said always, if you take your protractor and you measure this angle, this will be a positive number. Maybe this angle is 20 degrees or something, or in radians, but you can assign a number to that angle. So you know that both angles are positive numbers. So let's start with 2. So angle 2 is a positive number, right? This, it's because the protractor postulate, right? You can assign a positive number to that aperture. And by the algebraic theorem, again, we know that angle, since angle 2 is a positive number, we know that angle 2 is our number C. So we know that angle ABC, or the measurement of that angle, must be greater than the measurement of angle 1. And this is by the algebraic theorem, right? This is by the algebraic theorem. As a homework, try to prove the other part. Remember that the other part is that the measurement of angle ABC is greater than the measurement of angle 2. I'm sorry here because I'm missing some notation in here. We should have measurement of angle, measurement of the angle, and obviously here, same thing, measurement of angle 2, right? Just to be like real clear on the notation that we need to use. So the measurement of angle 2 here, also the measurement of angle C must be greater to the measurement of angle 1. Now we need to be really careful with the notation. I was just talking about it and maybe I forgot to put them, but you need to put them. You need to write it down. So let's try to do, or you try to do the other 2 lines for the measurement of angle ABC greater than the measurement of angle 2. It will be like your homework after this video. Okay, so see you in the next one.